It's another beautiful day in sunny Southern California. Perfect day to practice working problems and using these tools that we're learning about here in our organic chemistry class. I want to encourage you to go to discussion sections. It's a great opportunity to practice, to study, to become good at solving the kinds of problems that I put on our exams. So take advantage of discussion section as a way to get better for the tests that we give. I wanted to talk about bromomethane, which does not seem to me like a super exciting molecule. And the reason why it comes to mind is when I was looking on the internet, I noticed there was an article on some publication called BuzzFeed that was querying, can you answer the questions on this high school science exam? And I think it was about science questions, and I thought, gee, I don't know if I can answer. I don't think I remember anything from high school. And here was one of the questions, which I was taken aback by the complexity of this question. I don't know if this is really the kinds of questions they were asking you in high school. The question is telling you methanol undergoes a substitution reaction using hydrogen bromide. Compared to methanol, the product of the reaction has and then you're supposed to know the product of the reaction in high school. Somehow, I don't know if you actually covered this in high school. What is the product of methanol plus HBr? And I don't know how much you went into the details of molecular properties. When you substitute, so you have to know that when you substitute methanol with HBr, that you get a bromo group where the hydroxy group is. One thing is clear, that if you replace hydroxy with bromine and you memorize the periodic table, you'd know that bromine has an atomic weight of about 80. There's no way that the bromomethane weighs less. It's got to weigh more. If you studied the physical properties of organic molecules and hydrogen bonding, you would know that methanol should have greater solubility than a bromoalkane. In fact, I would expect, based on my personal experience in the laboratory, that haloalkanes are very greasy molecules, very nonpolar molecules. And if you had covered in your high school classes something about the molecular geometry of carbon-based molecules that are sp3, you'd know that these are near tetrahedral for both of those carbon atoms. So it really has to do with boiling point. You can't actually know, unless you've memorized some boiling points, that making something heavier still, right, heavier molecules have higher boiling points. But unless you've memorized some numbers, you couldn't actually know that bromomethane is still, has a lower boiling point than methanol. Bromomethane is a gas at room temperature. So I thought this was a particularly challenging question. But as I thought more about this, I wondered, why would any person on the planet Earth synthesize bromomethane in this way? I looked back at the Reaxys database, which has all the reactions recorded back to the 1850s, and nobody had ever actually done this reaction. Why would you take an expensive, corrosive gas like HBr and use that as your way to synthesize bromomethane? That's not how it is synthesized. The closest I could come to finding somebody who had done this is somebody took deuterated methanol because they were trying to synthesize deuterobromomethane, and they did this on a very small scale. Some physical chemists did this so they could study it. So where do we get bromomethane from? It's used as a fumigant to, like if you see homes where they're exterminating termites, they're putting bromomethane gas in there to kill the termites and the pests. The way they make that industrially is through this reaction. They take methanol, I'm showing you the balanced equation, bromine gas, and they're adding elemental sulfur to that. Now, they're not adding elemental sulfur for no reason. It turns out that sulfuric acid is a byproduct of this reaction, but this is not it's not because they're simply synthesizing HBr in their reaction mixture. The mechanism is extraordinarily complex and probably involves a mechanism like this, an SN2 type displacement of some sulfite leaving group. And you may not remember this, but you've covered a very similar mechanism before. When you covered the chemistry of SOCl2 and pyridine, replacing alcohols with chlorine, right? You saw SN2 type displacements of primary alkyl groups to displace chlorosulfites. I meant for this to be a chlorine atom here. To displace chlorosulfites And that's how you synthesize alkyl chlorides using SOCl2 and pyridine. So I thought that was a deep question. I don't know. I'm sure I couldn't have answered that when I was in high school. I don't know about you guys. And the other questions on that things were about subatomic particle physics, muons, leptons. I don't know what classes you guys had in high school. That's not the classes I had. So congratulations to any of the high school students who are getting these questions right. Maybe that's just a different country or something. Let me bring you back to where we're at right now in this chapter. It's chapter 18. I told you you have to memorize these 5 transformations. You just got to know the recipes for these. You've got to know how to make cyanohydrins, adding HCN across carbonyl groups. That's ketones and aldehydes. This chapter is ketones and aldehydes. And all the rest of the 4 transformations are condensation reactions where we're losing the element of water. We're adding to the carbonyl groups of aldehydes and ketones, and we are losing the elements of water. We're doing that to form imines. We're doing that to form enamines. The first thing we covered was condensations to make alkenes using the Wittig reaction. And what we're going to do now is we're going to talk about adding oxygen-based nucleophiles like alcohols and water to aldehydes and ketones. And that is tough because water is not very nucleophilic. And I'm sure you're all remembering, it's like, well, wait a second, I added water to carbocations. Well, that's a carbocation. Anything can add to a carbocation. So let's talk about what it takes to get an alcohol or water to add to an aldehyde or ketone. And I'll start off by reminding you that we've got an advantage here, and that is that aldehydes and ketones can be relatively reactive relative to esters and amides, but aldehydes especially. Let's go ahead and take a look. I want to start off by talking about a basic equilibrium process where water, just simple water, can add to aldehydes and ketones. And I'm going to start off with a simple molecule, acetaldehyde. And if we put a molecule of acetaldehyde in water, you'll very rapidly establish an equilibrium. You can't stop this equilibrium from occurring, where you add the elements of H2O across that carbonyl. And we generate a product, I'm not sure I should call it a product because it's not like you could isolate this, called a hydrate. It's also called a geminal diol, geminal meaning both of the OHs are attached to the same carbon, but hydrates is the more common term that a synthetic organic chemist, that an organic chemist would use. And this is not a useful transformation in organic chemistry. And I'll explain below here why it's not useful to anybody. And the key idea here is that it's an equilibrium process that you can't stop. Now, how much of this product you have is determined by the chemical structure of your carbonyl group. So everything depends on how much of that hydrate you get. Depends entirely on what is substituted to that carbonyl carbon on this aldehyde or ketone. So if you look at the amount of hydrate that you have at equilibrium, it depends on these R groups. So for formaldehyde, formaldehyde is an insanely reactive carbonyl compound. You can't actually buy formaldehyde. You can't put formaldehyde in a bottle and have it stay formaldehyde because formaldehyde carbonyls are so reactive, the oxygen of one formaldehyde will add to the carbonyl of another, and you get polymer and oligomers, and you get a nightmare. So formaldehyde is just not really representative of any normal aldehyde. At equilibrium, if you put formaldehyde in water, it does not exist as formaldehyde. It exists as this geminal diol, this hydrate called formalin, and you buy it like this. Like if you want to fix cells by reacting the proteins with this aldehyde, you're actually buying a solution of this hydrate molecule in methanol called formalin solution. Now that is the only aldehyde that gives you high yields of this hydrate. If you take acetaldehyde like I showed you above, at equilibrium, you've only got 58% of the hydrate at equilibrium. That means 42% of it exists as the starting material. And you can't change the equilibrium constant for this, right? If the equilibrium constant is 58 to 42, all you can do is accelerate the rate at which you reach that equilibrium, which is going to be 42 to 58. You can't increase the yield. You can't change the equilibrium constant for this reaction. All you can do is get to that equilibrium ratio faster. So you can't ever synthesize this geminal diol, this hydrate of acetaldehyde in good yield. And when you get to a typical ketone like acetone, you're never going to have very much present under these conditions. It's going to be about 0.2% at equilibrium. If you put acetone in a bottle of water, you're very rapidly going to reach this equilibrium ratio. You can't synthesize this in high yield. So why are we showing this to you? It turns out that these hydrates, these geminal diols, are important for helping us think about another class of molecules or functional groups called acetals. So we're not ever going to be able to make hydrates efficiently, but thinking about hydrates is really useful mechanistic thinking for teaching you about the fundamental chemistry of glycans, glycobiology, and synthetic intermediates. Let's go ahead and take a look at, at what's happening in this reaction. I'm going to show you a mechanism for this reaction. There's two different ways to accelerate this reaction. One way to accelerate this is to add acid, to have water and an aldehyde or ketone under acidic conditions, or some acid that is present. Another way is to use base, and what I'll talk about shortly is that nobody cares about the base catalyzed mechanism. So the only thing you really need to know, and you need to know this, you need to know the acid catalyzed mechanism for this reaction. So if I take some sort of an aldehyde or a ketone, and I have that in the presence of water, there's going to be an acid catalyzed reaction. And you might say, well, if I put this in neutral water, there's no acid in there. Yes, there is. There's not much, but it doesn't take much. Do you guys remember back from general chemistry talking about the ion product constant, where you learned the concentration of hydronium ion in neutral water is about 10 to the minus 7? You know, for most organic reactions, that's not useful for anything. The concentration is too low. But when it comes to hydrate formation with aldehydes, that's enough. That's enough. That's a high enough concentration. And step one here is we can't get water to attack this carbonyl directly. Water is not a good enough nucleophile. Yes, water and alcohols can attack carbocations, but not aldehydes and not ketones, and certainly not esters or amides. So we need to catalyze this reaction by making the aldehyde carbonyl more reactive. And so once we convert this into an O+, now it's very easy to add to that carbonyl. We refer to this species as an oxonium ion. What does that mean? Oxonium ion means 3 bonds to oxygen. That's all it means. It could be 3 single bonds. It could be a double bond and 1 single bond. It's 3 bonds to oxygen. There's got to be a positive charge on there. It's called an oxonium ion or an oxonium cation. And that carbonyl carbon is very electrophilic now. Super electrophilic. And now a pathetic nucleophile like water can easily add into that. Water, alcohols. Now you don't, right, this is equilibrium. You protonate the carbonyl, you take the proton off. You protonate the carbonyl, you take the proton off. In the short, brief amount of time that carbonyl is protonated, it's very easy for a water molecule or an alcohol molecule to attack that. And so now this makes a new carbon-oxygen bond. Now I'm going to draw the OH bonds here because you can tell I have to remove one of these protons from that oxonium, the new oxonium O+. So let me go ahead and draw out our A-, the conjugate base that's left over from our acid, because I'm going to use that to regenerate my acid catalyst. I'm going to use A- to pull off that proton, and now we've regenerated our acid catalyst, and we've generated that hydrate functional group. And this is equilibrium. The reaction, the acid is also, right, I've got my acid right here, just sitting there, waiting to protonate, right? I can't stop this acid from reprotonating the oxygen and driving the reaction back. It's an equilibrium. The acid catalyzes the forward and the reverse reactions equally well, right? There's only one transition state going from one intermediate to the other, and the acid helps you get back and forth. So you can't change the equilibrium constant, but acids can affect the rate at which you establish that equilibrium. Now, base you can accelerate this reaction by adding hydroxide anion, because hydroxide anion can easily add to a carbonyl. But I promise you, once you start adding bases and sodium hydroxide to aldehydes and ketones, you aren't going to care about hydrates. There's a whole class of chemistry called enolate chemistry that we cover in a couple of chapters. We cover in great detail, and that's what you're going to care about once you start adding bases to aldehydes and ketones. Okay, so you need to know this mechanism. It's fundamental, and I'll show you some related mechanisms in just a second here. Now, if it's not interesting to synthesize these hydrates by adding water to aldehydes and ketones, what do we care about? Let me show you what we care about. What we care about is taking aldehydes and ketones and adding not water, but alcohols. And I'll give you a typical example here. We're going to add methanol. And the product that we get out of this reaction, if we set it up just right, is to add alkoxy groups to that carbonyl. And we call this functional group an acetal. This is an acetal functional group. It used to be that people would distinguish, they would say, oh yeah, ketones give you ketals, aldehydes give you acetals, and you know what, you don't need that nomenclature. The book is very smart about saying, you know what, we're just going to call all of these acetals. Doesn't matter whether both R groups or alkyls, or one is an alkylate and one is an H. We're just going to call them acetals. All right, so you can tell that I've added two equivalents. The stoichiometry here is that I must have had two equivalents of this alcohol starting material, because I've got two methoxy groups on there. But that's not enough. If you really want to get an efficient reaction here, and the problem is this is really just an equilibrium, you have to use a vast excess of your alcohol. And you have to write the word excess there, because this is an equilibrium process, just like hydrate formation. And you have to drive that equilibrium using Le Chatelier's principle by adding a whopping, the fact is you use the methanol as a solvent in these reactions. Why is that? Because carbonyl groups are stable, C double bond O. Nature doesn't want to get rid of carbonyl groups and replace it with single bonds. The carbonyl group, like CO2, global warming, that's like the ultimate stable molecule. Now, this is a slow process, so how do we speed this up? The way we speed this up is we add extra acid, and we don't just add any acid. You could add other acids here, but we have to be very careful about the acid we add. If you add HCl, you're going to start getting chlorine anions adding to things. We don't like adding HBr, HCl, because bromide, chloride, iodide, those are nucleophiles. And we don't want those acting as nucleophiles in our reaction. So we want acids that have non-nucleophilic counterions. And the acid that we show you, I'm going to write the word catalytic. The acid is a catalyst, is going to be para-toluene sulfonic acid, PTSOH. Down below, I'll show you that that's one of many possible abbreviations. And I'll show you that it's a reaction, this is a compound that you ought to be very familiar with. So para-toluene sulfonic acid, as far as I know, that's the only acid catalyst they show you in this book. You could use others, but you can't use HCl, HBr, or some sort of mineral acid. Yeah, what? Well, we'll walk through the mechanism. The mechanism is quite complex. There's a byproduct here, and that byproduct is water. And so this is where, this water is where this ends up. So you take two H's from your alcohol molecules and the oxygen from the carbonyl, and after a long, crazy-ass mechanism, which I'm going to make you know, you end up losing water. All right, so we need toluene sulfonic acid. Why do we use toluene sulfonic acid? Because the conjugate base, toluene sulfonate anion, is not nucleophilic. Iodide is nucleophilic. Bromide is nucleophilic. Chloride is nucleophilic. But toluene sulfonate anion is not going to attack anything. We don't have to worry about that. So why do we use this? We use this because it's a convenient analog of sulfuric acid. So in organic chemistry, you're not going to find very many reactions where we're dumping catalytic sulfuric acid into our reaction mixtures. That's because sulfuric acid is this corrosive liquid. It's corrosive, it's not easy it's goopy, and we don't like, if you just have to measure out 2 milligrams of your catalytic acid, you don't want to be sitting there trying to measure out 2 milligrams of a goopy, sticky liquid that's corrosive. So we like to use solids that we can weigh out on a balance. And that's why we use toluene sulfonic acid. It's a convenient solid. It's like, hey, I need 2 milligrams. You just go weigh out a few flecks on the balance. You got an accurate mass, and then you just dump it into your reaction. So that's why we like this. The other reason we like this, it is inexpensive to make. We taught you how to make this. You probably worked problems where you synthesize this. And on an industrial scale, all you have to do is take the industrial solvent toluene and use your secret recipe, SO3, H2SO4. They do this on an industrial scale. They make zillions of tons of toluene sulfonic acid. Now, the sulfonic acid that they sell you has the methyl group at the para position. You know, if you abbreviate this, and I might abbreviate this as TSOH, this is such a common acid catalyst that a lot of synthetic organic chemists like me will drop the para P symbol. We just write TSOH, and every chemist understands that it's the para-substituted isomer. That's the one that they sell that's inexpensive. We have buckets of this in every lab here in the Department of Chemistry in the organic groups. Okay, so we use toluene sulfonic acid as the acid catalyst for this transformation. You could use sulfuric acid. Nobody does that. And we can replace carbonyl groups with 2 single bonds to alkoxy groups, and we call that an acetal. Now, the equilibrium isn't great. Boy, it is tough. It is tough to add, to replace carbonyl groups. Carbonyl groups are kind of the thermodynamic sink. So if I take some sort of an aldehyde, like benzaldehyde, or cyclohexane carboxaldehyde, or butanal, some sort of an aldehyde, I've got to add excess ethanol, methanol, or ethanol to make this work. Since you're adding an excess, you want cheap alcohols. You've got to have cheap alcohols for this to work if you're just going to want to add 2 alkoxy groups. And that basically means it's going to be methanol or ethanol. Those are the only 2 cheap ones. Never seen anybody do propanol. Never heard of it. It's only those 2. And how do you use it as excess? Well, you use it as the solvent. And if you write methanol over here as a reagent, you have to write the word excess. Sometimes people write the letters X and S. That's well understood to mean excess reagent. But, you know, when you've got excess methanol or ethanol, everybody understands that when you write that under the arrow, that means it's the solvent. And if it is the solvent, it is understood to be an excess. You don't have to write the word excess next to the solvent. So if your solvent is your reactant, you don't have to write the word excess, and you indicate that by writing it under the arrow. If you write sodium chloride under the arrow, everybody will know that that can't possibly be the solvent. So it's only if you write a common solvent molecule under the arrow that everybody understands that to be the solvent and present in excess. Okay, what's our acid catalyst that we need for this? It's going to be toluene sulfonic acid. I often like to write the word catalytic next to that, just to make it clear we're not trying to add tosylate groups to our products, right? It's just a catalyst to accelerate the reaction of the aldehyde with the methanol. You don't have to write the word catalytic here. At the beginning, I kind of like to do that, so you're not trying to figure out where's the tosylate group in the product. No, if you want to make a tosylate, you use tosyl chloride and pyridine. We taught you about that in the first quarter of organic chemistry. So this will convert the aldehyde into an acetal. These conditions. And you have to use excess. It's just absolutely required to use an excess of the alcohol because you're driving the equilibrium using Le Chatelier's principle. Okay, we have a trick. You know, you still don't get great yields. Again, this is still an equilibrium process, and we still have to worry about the backwards reaction. It's very hard to drive. The actual fact of the matter is that we are typically either trying to boil off the water using special apparatuses to remove water, or we're dumping in these dehydrating agents into our reactions that soak up water, these clay-like materials called proton sponge. Just tricks to get rid of the water to drive the equilibrium. But really, if you want a good equilibrium, you want to make rings. You know, I often write questions on my exams where you cyclize things to make rings with Friedel-Crafts, or you break open rings, and you might think, what's this deal with Van Vranken and his rings? But rings are favorable. When you have reactions that cyclize and make 5- and 6-membered rings, those are highly favorable. So one trick we use to generate, if we don't really care about these groups here and we just want to make some kind of an acetal, right? Suppose I don't want a carbonyl group floating around in my reaction because I know it's going to react with a Grignard reagent. I can hide that carbonyl by converting it into an acetal. And so let me show you, this is not a common acetal to form, but it's a good starting point for helping us talk about acetals. Let me show you a common acetal structure. A common acetal that's easier to make in high yield would be a cyclic acetal. So if I wanted to take some sort of an aldehyde like benzaldehyde and convert that into an acetal, instead of using a big excess of methanol, we use a diol, a 1,2-diol. This one is called ethylene glycol. I forgot the IUPAC name for that, but ethylene glycol is the common name. And the reason why this is an efficient acetal forming reaction is because the acetal is cyclic. It's much more stable than an acyclic acetal with 2 methoxy groups. So 1,2-diols generate stable 5-membered ring acetals, and 1,3-diols generate stable 6-membered ring acetals. And so that ring makes this a much more stable acetal, having that 5 or 6-membered ring there. Now, why would you do that? The reason why you would do that is, let's suppose I wanted to make a Grignard reagent out of this. Well, I can't be making Grignard reagents when when every molecule in my flask has an aldehyde on the other side. The Grignard reagent on one molecule start going to attacking aldehydes on the other molecules. Right? If you wanted to make a Grignard reagent out of this, you've got to mask somehow that aldehyde. And this is exactly how you would do that. Now you can make a Grignard reagent. Once you protect that aldehyde as an acetal, you can go to town. You can add butyllithium, magnesium, lithium aluminum hydride. None of those things will touch this acetal. The only thing that is going to mess with that acetal is acidic conditions. So you can use the craziest, most basic conditions you want, and you're never going to touch that acetal. Totally resistant to any base, any nucleophilic attack, nothing. Won't touch it. Acid, though, boy. You touch that with acid, poof, it's gone. Let's go ahead and talk about the mechanism for acetal formation. Seems like a lot of work, but we've got to walk through this mechanism. First, I just want to step back and show you that it looks kind of like that hydrate mechanism. We're just going to look like we're doing the hydrate mechanism over and over. So if I take some sort of a ketone or an aldehyde, right, we've already talked about how you could make hydrates out of aldehyde and ketone carbonyl groups. So we're going to walk through this mechanism, but there's 2 stages to this mechanism. The first stage is we're going to add 1 alcohol molecule. I'll show you the mechanism for that, for how we add 1 alcohol molecule to the carbonyl. And we make this intermediate that has an important name, and I expect you to know this name. And this species is called a hemiacetal. And you need to know that name. It's called a hemiacetal. It's got 1 hydroxy group still there. The carbonyl group is still attached as an OH, and we've only added 1 alcohol molecule. And then there's a further equilibrium where we do an SN1 reaction and we replace the second OH group with another alkoxy group. And this we call an acetal. This is a fully formed acetal. So you need to know this name, hemiacetal. Hemi means half. It's half-ass, half-acetal. They don't call it half-acetal, I guess because it doesn't sound polite. And we're going to walk through the mechanism for these 2 stages. The first one is kind of like diol, the hydrate formation. The second one is an SN1 reaction, which you ought to know, but it's always good to review that. All right, let's walk through the mechanism for this process of going from an aldehyde or a ketone all the way to an acetal. And we're going to have to, if we want some sort of water or an alcohol to attack a carbonyl group, I'm going to stick the carbonyl on its side now. We've got to protonate that carbonyl group. We're not going to get water or an alcohol, in this case an alcohol, an OH group to attack that carbonyl unless we protonate the carbonyl. It's the only chance we have to get acceptable rates of addition to that carbonyl group. Whoop. And if you're thinking, well, I don't want to memorize this new process of protonating carbonyls. So when we get to chapter 20, you're going to be doing this left and right to get alcohols and water to attack ester carbonyls. You've got to protonate carbonyls. All right, so now we've got this protonated carbonyl, and now it's very easy to attack the carbonyl carbon once it's an oxonium ion, once it's protonated. So now we get good rates of attack. We don't have very much of this protonated carbonyl in solution, but for the few molecules that are protonated, so easy to add any kind of a nucleophile to that carbonyl once it's protonated. And so now this gives us our two bonds to oxygen atoms. We still have this proton sticking down here on the bottom. We have to get rid of that. We still have A- floating around. I'll draw it down below here because you can see I'm going to protonate. And see how I wrote that HO bond? I've done this mechanism enough times that I know I'm going to need to break that HO bond on my oxonium ion. So I'll come along here and deprotonate. And that now leads us to our hemiacetal intermediate. And we've regenerated our acid catalyst, right? When I use A- to pull that proton off, but watch this. I've done this mechanism so many times that I know to draw that acid catalyst on top. Because now, yes, you could put the proton back on RO, but that's just going to drive you backwards towards the starting materials. What I want to do is explain with my mechanism how we replace the HO. So I'm drawing the HO on top now. Does that mean we're not protonating RO and going backwards? Yes, everything's in equilibrium here. I'm just trying to show the steps that take us towards the acetal product. So now we've protonated that OH group to make it into a leaving group. And the second we do that, boy, this alkoxy group has just been laying around here, just waiting. This thing is just waiting for you to protonate that OH. The second you protonate that OH, that alkoxy group is going to push out the OH. Just waiting here. Boom. It's like an SN2 reaction a little bit, but it's better, right? SN2 reactions, things have to collide with each other billions of times before you finally form a bond. That lone pair is right there all the time waiting for you to protonate that OH. And once you protonate the OH, it's out of there. And so now we end up with this intermediate that looks a lot like this intermediate right above. You get an oxonium ion. And guess what? Another alcohol is going to attack that oxonium ion. This intermediate here should look a lot like the intermediate above. Right? Once you understand that protonating an O, a carbonyl oxygen, makes it a better electrophilic functional group, then it's easy to understand why it's easy for alcohols to attack this oxonium ion here, where there's an alkyl group on the O+. So easy to attack that. And you can see that the next intermediate kind of looks similar to the one above. And I'm going to try to draw this in that way to emphasize this similarity. And we still have an H on the alcohol that just attacked. Got that oxonium ion, and so now we're going to I'm not really happy with the shape of that plus charge there. And so now we use our A- to deprotonate this. So the top row of this mechanism should look very similar to the bottom row of this mechanism. And it should all look very similar to the mechanism for hydrate formation. And so this is the mechanism for acetal formation. So first we're making a hemiacetal, and then in the second step we're doing this basically an SN1 type reaction. All right, so that's the mechanism for acetal formation, and you have to know this mechanism. It's kind of like forming a hydrate twice over or something. Okay, let's take a look at this idea that we can protect carbonyls as acetals and prevent them from reacting. So let's suppose I wanted to take this bromoalkane here and form a new carbon-carbon bond. You guys know how to make carbon-carbon bonds using Grignard reagents. So if I wanted to synthesize this bond right here, well, that's clearly going to involve some sort of an alkylithium addition or a Grignard reagent. The problem is this stupid, annoying aldehyde on the other side. We can't start making Grignard reagents if there's this annoying aldehyde group on the other side. And so this is a case, if we wanted to do this synthetic transformation, we need to protect this aldehyde on our bromoalkane so that it doesn't react with any kind of known nucleophile that we teach you about. So the first thing we're going to do is we're going to convert the aldehyde in this, let me make this clear, I'm not reacting the acetaldehyde yet. We're just taking that bromoacetaldehyde without the acetaldehyde there, and we're going to convert that into an acetal. And I'm going to make a 5-membered ring acetal because people don't make methoxy acetals. The equilibrium is not great enough. But making 5-membered ring acetals, that's the one kind of acetal synthetically that's useful as a protecting group. And so now, if we do that, we're going to have only sigma bonds now. We're going to have this 5-membered ring acetal where we used to have an aldehyde, and now no base will touch this acetal. No nucleophile will touch that acetal. We can do all kinds of Grignard reagent chemistry in this reaction mixture, and there's no carbonyl groups now as we're making our Grignard reagent. Now, do you remember the reaction conditions for making Grignard reagents? It's magnesium. Or if you wanted to make alkylithium, you had lithium metal. The Grignards are more common in a laboratory like this. On an industrial scale, the lithium stuff is easier to do. Okay, so we're going to make a Grignard reagent here, and now we've got this amazing nucleophile. There it is. Our carbon-bromine bond is now a supernucleophilic carbon-magnesium bond, and it doesn't matter that it's nucleophilic. That acetal is not going to touch it. You can't use base to remove acetals. You can't use nucleophiles to remove acetals. You can't do SN2 reactions on acetals. When you want to remove that acetal, you use acid. And I'm not putting any acid in here. Okay, so the next thing is we want to make that bond, a carbon-carbon bond, by adding a carbonyl. Now we can come in with our acetaldehyde. Step 1. Step 2, we do an H2O workup. We don't do an HCl workup. I guess in theory we could combine the next step. But this is going to lead to a new carbon-carbon bond. So if I start over on this side and I start drawing that alkyl chain, don't worry about the stereochemistry here. I'm just trying to show the bond-forming events. And now that we're done with this aldehyde, with this acetal thing, we want to remove that. And so now, if we want to remove this, we just change the conditions. H2O, instead of adding an alcohol, we add water because we're going to hydrolyze back to the aldehyde. And you could write toluene sulfonic acid just to remember that sulfonic acids catalyze the equilibrium, and the equilibrium lies heavily towards the carbonyl. So you just swamp it with an excess of water. In fact, in these cases, it is so easy to hydrolyze things back that you can get away with HCl. And I think the book uses, and we do this in our lab, we use it, because everybody has a bottle of HCl. It's so fast to go back towards the stable carbonyl that we can get away with HCl here. So if you wrote HCl, I wouldn't count that wrong. If you wrote toluene sulfonic acid, I feel like that makes more sense since we're using toluene sulfonic acid to catalyze formation of acetals. It makes sense to use toluene sulfonic acid to catalyze equilibrium cleavage. But again, if you wrote HCl as your catalyst here, that's actually very common. All right, so acetals are useful as protecting groups. You can use them to protect carbonyls, aldehydes and ketones, not esters. This chapter is about aldehydes and ketones. Now I want to come back and talk about hemiacetals. It turns out they are incredibly important, especially in biochemistry and biology. And generally, you cannot isolate any hemiacetal intermediate if it's acyclic. Right? If I try to make something like this, if I try to make some sort of a functional group like this, it would be completely unstable. You couldn't isolate that. There's no way to obtain that, work with it. It would be in equilibrium with the starting carbonyl. But for cyclic hemiacetals, they are sufficiently stable that you can isolate them and work with them. So if I take a hydroxy group that is 5 or 6 atoms away from the carbonyl, like this, these two groups, this oxygen is 5 atoms away from the carbonyl, you can't stop those two from colliding with each other. You end up with rings that are stable, hemiacetal rings. It would be completely unstable if it was acyclic, but because this is a 5 or 6 membered ring over here, that turns out to be sufficiently stable. Let's take a look at the equilibrium amounts. So what would happen if this oxygen atom and this carbonyl group were 4 atoms away and we tried to make a 4-membered ring? You're not going to have any stable cyclic hemiacetal out of that. Less than 1% of your hydroxyaldehyde would exist in the ring form because 4-membered rings are strained. Bond angles don't want to be 90 degrees, they want to be 109 point something, right? You don't want 90-degree bond angles in a carbon-based ring. But 5-membered rings are pretty good. For this system, 89% of this hydroxyaldehyde, if the oxygen was 5 atoms away, would exist in the hemiacetal cyclic form. And if it's a 6-membered ring, it's mostly, it's even better. 94% of it. It's not like you can stop it from cyclizing. If you somehow synthesized this molecule over here using an ozonolysis reaction or half of a PCC oxidation, it would immediately form the ring. You can't stop it from happening. You can't change the equilibrium constant. That's not determined by you. You can just accelerate the rate at which you reach equilibrium. Now, if you want to talk 7, 8, 9-membered rings, those are generally not good. So, we're in the best case for best ring sizes, it's still less than 20%. So these are the good ones. Generally, if you can cyclize to form let me take that blue arrow out. If you can cyclize to form a 5 or 6-membered ring, if a hydroxy group is 5 or 6 atoms away from an aldehyde, you're going to cyclize to make a cyclic hemiacetal. What's the mechanism for this reaction? It's just like the hemiacetal reaction I showed you before. Let's go ahead and draw out this mechanism. So if I draw this, I'll do the 6-membered ring case here. These are acid-catalyzed reactions, even in neutral water. And so if you got some sort of a hydronium ion or some sort of acidic species that has a proton on there, and we're going to protonate that carbonyl in order to generate a protonated carbonyl, or more specifically an oxonium ion. Most people call it a protonated carbonyl. And now it's very easy to attack that protonated carbonyl. And that hydroxy group is colliding over and over and over again. It can't get away. You can't stop these collisions from occurring to form these carbon-oxygen bonds. And now we have this proton on our OH that attacked. I've done this mechanism many times, so I know to draw that OH bond because I'm going to cleave that bond using A-. So now I come along with my conjugate base left over from my acid, and I deprotonate that, and that's the mechanism for hemiacetal formation. It's not that exciting because it looks just like the mechanisms I've just shown you for hydrate formation and for acetal formation. The fact that it's a cyclic molecule doesn't make it any different from the other mechanisms. Now, hemiacetals do SN1 chemistry, right? I told you that the mechanism for acetal formation involves this formation of a hydrate kind of thing, followed by an SN1. And so hemiacetals like this are susceptible to SN1 chemistry. And let's go ahead and take a look, because there's 2 different carbon-oxygen bonds here, but really only one of them is going to engage in SN1 chemistry. And here's what that looks like. If I take a hemiacetal, one of these cyclic hemiacetals, like this, well, we can treat this with catalytic acid. And these are conditions that you learned back when you did SN1 reactions in the first quarter of organic chemistry. You take some sort of an acid catalyst here. Catalytic HCl is the common one. And then you put methanol into the solution, and you can do an SN1 reaction. And you go through a carbocation, we might draw that in a different way, so you get addition to both top and bottom faces of that carbocation. If I have a box here and I say draw the product in the box, then you need to clearly indicate the stereochemistry. SN1 reactions give you equal rates of attack from the top and the bottom, and so you'll get a mixture of enantiomers there. So you need to recognize that you've generated a stereogenic center. And we can hydrolyze these cyclic hemiacetals or cyclic acetal products under the same types of conditions. So down below here, you can see that we've got potentially two bonds we could cleave, but it's going to be the exocyclic bond, the one outside the ring that cleaves. So all we do is replace our alcohol solvent with water, and now we can cleave these external groups. And it doesn't matter whether the ethoxy group started off wedge or dash, doesn't matter. We're going to get a mixture of these products. And if I asked you to draw the products in the box, you have to draw the ethanol as well, because I want to see where the carbon atoms in the starting material end up. You have to account for all those carbon atoms that were in the starting material if I say draw the product in the box. This chemistry right here is fundamental to the chemistry of nucleotides and nucleosides. Nucleotide subunits of DNA are enzymatically made, so if you haven't noticed it already, this should look very much like ribose, the ribopyranosides that are present in nucleotide subunits of DNA. And that's why this chemistry is important. And these subunits here are going to look very much like, I'm not quite sure how much of this you've covered in your classes, like glucose, galactose, xylose, all of the sugars that you find coating the proteins, that are proteoglycans and glycoproteins on the surfaces of proteins that are important in cell recognition, those are all synthesized through this type of SN1 chemistry to form these bonds. That's how sugars are linked together in glycogen and in glycoproteins. Okay, that's it for Chapter 18. What is Chapter 18? Chapter 18 is those 5 recipes. So cyanohydrin formation. We talked about the Wittig reaction. We talked about imines. We talked about enamines. And then last, we've talked about addition of oxygen nucleophiles to make acetals and hemiacetals. And you need to practice this chemistry. When we come back, we're going to be talking about a whole chapter on carboxylic acids and nitriles, functional groups where there are 3 bonds to heteroatoms. And there's, and I think and hope that we will finish that entire chapter in one lecture. It's not a lot to cover in there.